We are given a graph of this relation and we would like to know if it's a function. To determine that, we could use the vertical line test. We take a vertical line and move it from left to right and just make sure the vertical line is not in contact with this graph at more than one point at a time. As we move it across, we're only in contact with one point at a time, so it does pass the vertical line test. So this relation is a function. Another way that we could look at it is, does each input x have a unique output y? That statement really means that we can't have 2 points where we have the same x in the coordinate. Here we're okay because our y's are the same, but we just couldn't have 2 points that start with the same x value. Next, we want to know, does the relation have an inverse that is a function? The first way that you could determine that is to conduct the horizontal line test. That's a lot like the vertical line test, but we're just going to move a horizontal line from bottom to top. If we have at any time when we move that from bottom to top, if we're in contact with 2 points at the same time, then it's not passing the horizontal line test. I stopped this horizontal line right there to show you that we are in contact with the graph in 2 spots at the same time. So since we are in contact at 2 points at the same time, it does not pass the horizontal line test. So this relation, it is not going to have an inverse that's a function. A second way to determine the answer to this question is, does every y have a unique x? Well, these same points we looked at a minute ago, notice that we have 2 y values that are exactly the same. So every y does not have a unique x. So no, so it is not, our inverse is not going to be a function. A follow-up question is often, is the relation 1-to-1? To be 1-to-1, it simply means that the answers to part A and B are both yes. Our original relation would need to pass the vertical and horizontal line test. So in this case, that's no. Let's go through the same series of questions to determine if this relation is a function. We can determine with the vertical line test, moving that vertical line from left to right, looking to see if we are encountering the graph at more than one point at the same time, and we are. We happen to be hitting the graph in 2 spots there. So the vertical line test fails, so we know this is not a function. A second way to think about that is, does each input x have a unique output y? So notice here that we have root 3 and negative root 3. We have 2 different y values for the same x value, -1. So no, this is not a function. Does the relation have an inverse that is a function? To answer that question, we can perform the horizontal line test, very similar to the vertical line test, moving that from bottom to top. I'm stopping it there to illustrate that we are in contact with the graph at more than one point at the same time. So the horizontal line test fails, so we know that no, the relation does not have an inverse that is a function. And then leaving those 2 coordinates there, we can look at it a different way. Does every y have a unique x? So notice here the y's are 1, but we have 2 different x's that go with the y coordinate 1. So again, we know that no, this relation's inverse is not going to be a function. The follow-up question is the relation known to be 1-to-1. Really, it's every x has a unique y, every y has a unique x. But our test there is if we were to answer yes to both part A and B, then this relation would have been 1-to-1. But since we didn't, no, it is not 1-to-1. Let's look at one more example before we move on. Is this relation a function? Performing the vertical line test, we are only in contact with one point at a time, so yes. Looking at it a different way, each input x has a unique y. That's true. Does the relation have an inverse that is a function? Let's perform the horizontal line test. We're only in contact with one point at a time, so yes. A second way to look at it is every y has a unique x, and so that is true. Is the relation 1-to-1? For it to be 1-to-1, this is going to have to pass the vertical and horizontal line test. You could also think of it as every x has a unique y and every y has a unique x. So since the answer to A and B were both yes, we know this relation is 1-to-1. Now that we can answer these three questions about the relation, and we found out that this relation is a function, we want to be able to graph the inverse of this relation. I called this relation f, and it's a function, so I'm going to refer to it as the function f. If you want to graph the inverse of this function, well, inverses are just a reflection across the y equals x line. So let me draw in the y equals x line, thinking about what y equals x looks like. We'd have coordinates 1, 1, 2, 2, 3, 3. All right, so we have this line y equals x. If we reflect this f function across this line, we will come up with the inverse function. The notation for f inverse is f to the negative 1. If I reflect the f across the y equals x line, it's going to look like that. Now, some of you are very visual people, and this reflection seems like common sense to you. But if you are not a particularly visual person, then you can go about this in a systematic way to draw the inverse of the function. We can use this inverse reflection principle, and it's saying that for every a comma b, that the inverse has the coordinate b comma a. So let's start from scratch here and say, all right, I want to draw in the inverse function. I'm going to start picking points moving from left to right across the function f. I'm going to start with this point right here. The coordinate happens to be negative 2, 4. That's a comma b, so b comma a would be 4 comma negative 2. When I reflect that across that y equals x line, I'm right there at 4 comma negative 2. I'm going to continue selecting points along that f curve at significant locations and reflecting them across. Connecting the points in order, I'm going to get the graph of f inverse. So here's another point on that f function, but notice we're right on top of the y equals x line, so when I go to reflect it, it doesn't go anywhere. So that would be my next point. Continuing along that f function, I get to this point, which also happens to be on the y equals x line. So when I reflect it, it's not going anywhere. Then let's do one more point. We're kind of as far to the right as we can on that f function. That coordinate happens to be at 2, 4. So if I reflect that point across the y equals x line, I just take 2, 4 and make it 4, 2. Now I've plotted several points in order, And if I connect them in the same order, notice I get the graph of F inverse. Since we have the graph of F inverse in front of us, let's look back for a little bit more meaning. Does the relation have an inverse that is a function? Well, this here is the inverse, but notice it would not pass the vertical line test. So when we did a horizontal line test on the original function, it's the same thing as doing a vertical line test after we've drawn the inverse function. Now that we can find the graph of F inverse from the graph of F, we want to find the equation for F inverse from the equation of F. If the coordinate a comma b is on the original function, then we know that the coordinate b comma a is on its inverse. In other words, just our x's and y's are switching places. So I'm going to write down the original function f of x. I just replace the f of x with y, just changing that notation, but otherwise notice I've written down exactly the same thing as f of x. Knowing that a comma b becomes b comma a, we're just going to swap out x's for y's and y's for x's. So this y is going to become an x, and this x is going to become a y. So our first step is to swap the x's and y's. Next, we want to solve this new equation for y. We can solve this equation for y by undoing the order of operations. So let's get rid of plus 5 by subtracting 5 from both sides. Next, I'm going to get rid of this cube by cube rooting both sides. Keep in mind you do not get positive and negative when you take an odd root of both sides. That only happens when you take an even root of both sides. Once we have cube root both sides, we've freed up this y minus 1 out of the parentheses, so we can undo the minus 1 with add 1. We now have the equation of f inverse of x, but we should have a little bit better notation, just like our original was f of x equals. This y is f inverse of x, so the final equation for the inverse function is f inverse of x is equal to the cube root of x minus 5 plus 1. All right, now let's go ahead and graph both f and f inverse on the same graph. You can head over to Desmos or grab your graphing calculator to do that. So here I've graphed f, and then there's the graph of f inverse. Notice that f inverse is the reflection of f over that y equals x line. Now, it is not an option to verify graphically. You need to do this step. I can tell you on the final exam, there is going to be a tricky one like this question. And let's go ahead and find the domain of f inverse. Let's look at our equation here of f inverse. Remember, when you want to find the domain, you're just asking yourself, do I see an x underneath an even root, an x in the denominator, or am I taking the log of x? The answer to all three of those questions is no. So that means the domain of f inverse is all real numbers, negative infinity through infinity. Now, this particular go-around, I said, graphing to verify is not optional, but everything seemed to work out. That is true in this case, but let's look at another one where that graphing to verify proves to be very helpful. Here we have the equation for f of x, and we would like to find the equation for f inverse of x. So remember, we just want to swap the x's and y's. F of x is the y, so that's going to turn into an x, and then this x right there is going to turn into a y. Okay, now that I've swapped the x's and y's, I'm going to solve this new equation for y. To get rid of the square root, I'm going to square both sides. Then I'm going to subtract 3 from both sides. And I now know that y equals x squared minus 3. This is the inverse function, but if we want to use really good notation, and we do, let's change that y into f inverse of x. All right, there we have the equation for f inverse of x. So next, let's graph both the equation we have for f and f inverse on the same graph. You can do that at Desmos.com, or you can do it on your graphing calculator. So here I have graphed both f and f inverse. Do you notice anything? If I put in that line y equals x, the graph of f inverse should be a reflection of the graph of f across the y equals x line. This parabola is too much graph. It is not the graph of just that one piece right there reflected across the y equals x line. So, as I said before, graphing is not optional. You need to perform that last step. I want to know what is the domain of f inverse. If I were to only look at the equation that we created for f inverse to determine the domain, you would look at this equation and hopefully say, well, I don't see an x in the denominator. I don't see an x underneath an even root. I'm not taking the log of x. So the domain of that is all real numbers. Well, there is more to finding the domain of an inverse than just looking at the equation of f inverse. We must graph both f and the equation that we got algebraically for f inverse, and then we might need to leave part of this graph that we got, this equation that we got, off of there. So if we are only going to keep the right-hand side of this parabola so that now that right-hand side is the reflection of this red one across the y equals x, we do that by limiting the domain. So we're only going to keep from 0 to infinity of the equation x squared minus 3 so that this piece is indeed a reflection of the y equals square root of x plus 3. On the final exam, there is a tricky question like this, where you will be asked to find the domain of the inverse function. And so those first steps are to swap the x and y, solve for y, but don't just look at that final equation to determine the domain of the inverse. Graph both the f and f inverse on the same graph and see if you need to leave some of the graph of, in this case, y equals x squared minus 3, leave it off so that when you leave that piece off, that this is the reflection of the original.